Hey there, welcome to this explainer. Today, we're going to explore what honestly sounds like a total contradiction at first glance. We're talking about intentionally sabotaging raw electrical power just to get total clarity. If you've ever wondered how your high-end audio gear or your delicate electronic instruments produce those super crisp, stable signals, well, you are about to discover the amazing paradox right at the heart of modern circuit design.
So why on earth make an amplifier weaker on purpose? When I first came across this concept, it completely blew my mind. I mean, in a world that is practically obsessed with more power, more gain, and more amplification, why would an engineer take an incredibly strong signal and just forcefully suppress it? Let's unpack exactly why sacrificing that sheer strength is the ultimate secret to high-fidelity sound and incredibly stable devices. Here's our quick roadmap for today. We'll start with the amplifier noise problem, move into the magic of negative feedback, and explore why we sacrifice power. Then we'll look at negative current feedback, the emitter follower circuit, and wrap things up with the Darlington Amplifier super pair. Let's just jump right in. Okay, first up, the amplifier noise problem, or why having way too much of a good thing is actually a really bad thing. Let's see how massive amplification quickly becomes an electrical engineer's absolute worst nightmare. The core issue here is that practical amplifiers are incredibly powerful. We are talking about a raw gain of nearly 1 million. That means the output is literally 1 million times stronger than what goes in. But because they're so ridiculously sensitive, even the tiniest, most casual disturbance, like a stray magnetic field creating a tiny hum, gets immediately multiplied into this massive, disruptive roar. It's kind of like holding a microphone way too close to a speaker at a karaoke bar. That noise is totally undesirable, making the raw amplifier essentially unusable in the real world. To tame all that chaotic, runaway noise, engineers use an incredibly elegant trick called feedback. It's a concept as old as the very first machines, but it really found its true calling in electronics. Simply put, feedback is taking a small fraction, just a tiny sample, of the final output energy and recycling it. You literally inject it right back to the starting line at the input. Which brings us to the magic of negative feedback and how we actually tame that chaos. Now that we've got the noise problem and the basic idea of looping signals down, let's see how different feedback flavors can either completely destroy a circuit's usefulness or totally stabilize it.
When you compare the two main paths we can take, the contrast is super stark. First, you have positive feedback. This is where the recycled energy loops back perfectly in sync, or in phase, with the input. It aids the signal, creating this crazy 360-degree loop of ever-increasing energy that quickly ends in horrific screeching and distortion. But then you have negative feedback. Here, the loop introduces a stabilizing 180-degree phase shift. The recycled signal arrives entirely out of phase with the input. It actively pushes back against the incoming signal. And honestly, that pushback is the magic ingredient for stability.
All right, so why sacrifice amplifier power? Let's talk about the big trade-off. If negative feedback is actively pushing against the input signal, it's inevitably going to force the overall power down. And that brings us to the core of our paradox. Just look at the sheer scale of the sacrifice we're making here. When we apply negative voltage feedback, we're not just trimming the power a little bit, we're intentionally taking a circuit with an open loop gain of 10,000, that's the amplifier without any feedback, and closing the loop to drop that amplification all the way down to a super modest 100. That is a massive, massive drop in raw power. Mathematically, it's actually pretty fascinating. By dividing that massive original gain by just a tiny 1% feedback fraction in the formula's denominator, the overall voltage gain gets absolutely slashed by a factor of 100. Because the original raw gain was so high to begin with, that tiny little recycled fraction is more than enough to completely alter the final output. So you're probably asking, why on earth would we surrender all that power? Well, in exchange, we unlock 4 absolutely massive engineering victories. First up, gain stability. Our amplifier becomes almost entirely immune to wild temperature changes or weird variations in the transistors themselves. Second, reduced nonlinear distortion, meaning loud signals won't get horribly clipped. Third, improved frequency response. so high and low pitches are treated equally. And finally, increased overall circuit stability. We are literally trading chaotic raw power for refined, predictable, high-fidelity control. But wait, it actually gets better. This mathematical trade-off does a miraculous balancing act on the circuit's impedance too. It dramatically increases the input impedance, which is huge because it means the amplifier won't drain the delicate source supplying the signal. At the exact same time, it drops the output impedance, making the amplifier effortlessly able to drive heavy, demanding loads like a loudspeaker. Honestly, it's a total win-win. Moving right along to a slightly different flavor, negative current feedback. Up to this point, we've focused entirely on voltage. But let's see what happens when we apply the exact same stabilizing principle to electrical current instead. What's super interesting here is that the underlying math is virtually identical to what we just went through. But instead of stabilizing the voltage, we're keeping the flow of current perfectly in check. By using a feedback resistor to return a proportional amount of current back to the input terminals, we lower the overall current gain. It perfectly mirrors the voltage stabilization we saw, letting us strictly control current flow without messing with the voltage gain at all. Let's take all these abstract theories and look at the ultimate buffer, the emitter-follower circuit. This is where we see a tangible, real-world hero of everyday electronics. What stands out right away with this specific setup is actually what's missing. Notice there is no collector load resistor at all. Instead, the entire output voltage is taken straight across the emitter resistance. Because of this, the full output voltage opposes the input voltage. It's essentially providing 100% negative voltage feedback. The output strictly follows the input, which is exactly why engineers named it the emitter follower. When you look at the extreme results of applying 100% negative feedback, it's pretty wild. Because it pushes back so incredibly hard, it produces absolutely zero voltage gain. The gain is literally hovering right around 1. But it compensates beautifully. It maintains a relatively high current gain, and most importantly, it delivers those fantastic impedance characteristics we just talked about: extremely high input impedance and very low output impedance. And this really reveals the emitter follower's true purpose. It isn't an amplifier in the traditional sense, it's what we call an impedance matcher, or a buffer. Imagine trying to connect a highly delicate signal source with 120 kilo ohms of resistance straight into a heavy-duty 20 ohm load. The signal would be completely crushed. But if you slip an emitter follower right in between them, it acts as the perfect bridge. It safely transfers maximum power from that delicate source to the heavy load without losing any signal quality whatsoever. Which leads us to our final component today, the Darlington Amplifier super pair. Because, the emitter follower is amazing, but what happens when just one isn't strong enough on its own? What if an engineer needs even more current gain and even higher input impedance? Well, to solve this, engineers came up with a brilliant trick. They cascade two transistors together in a very specific sequence. The emitter of the very first transistor connects directly to the base of the second. This essentially forces the output current of the first transistor to act as the primary, highly amplified fuel driving the second one. It's basically a chain reaction of amplification. By directly coupling them like this, these two distinct components combine forces to act functionally as one single super-powered transistor. And here's the kicker. Because the first feeds the second, the overall current gain isn't just added together. It is the multiplied product of both individual gains. So if each transistor has a gain of 100, your total gain skyrockets to 10,000. Thanks to this exponential multiplication, working together as a Darlington pair achieves some remarkably extreme characteristics. We can reach an outrageously high input impedance, like 16.17 megaohms in some textbook examples. That is phenomenally better than what any standard single transistor could ever provide all by itself. The math completely backs this up, showing exactly how these dual transistors, which are often just packaged together in a single housing with 3 terminals, function in tandem. Inside, those internal negative feedback mechanisms and direct couplings are doing all the heavy lifting. They unlock thousands of times more current gain while remaining perfectly stable and presenting practically zero load to the original signal source. It truly is engineering elegance at its absolutely finest. as we wrap up this explainer today, take a second to think about the smartphone in your pocket or those noise-canceling headphones you use. They rely completely on this paradoxical magic to function day in and day out. It really makes you wonder, what other incredible technologies in our everyday lives only achieve their true power by intentionally holding themselves back? Thanks so much for exploring this with